All right, y'all. In this video, we are going to be covering section 3.1. So we're going to talk a lot about in the next few sections about how we use derivatives in graphing. So the next three sections are really all about graphing. So section 3.1 is titled Using First Derivatives to Classify Maximum and Minimum Values and Sketch Graphs. So a lot of first derivative stuff today. Lot of notes to take. So at any point you need to pause this video and get the notes written down as I talk through them. Please do that because there is a bunch of information I'm about to throw at you in the next 10 minutes. So here we go. First theorem I want to go over. Let f of x be a differentiable function over some open interval I. So the first definition or theorem we need to go over is what does it mean if your first derivative is either positive or negative? So if your first derivative of your function is greater than 0, which for us means positive, that means that your original function is increasing on that interval. So let me say that again. If your first derivative is positive on an interval, then that means your original function is increasing on that interval. Versus if your first derivative is less than 0, which to us, that means negative, that means on that interval, the original function is decreasing. So you got to make sure positive means increasing on the first derivative, negative first derivative means decreasing. So as you can see down here on this little illustration I pulled out of the textbook, there are two intervals up here, or three intervals. This first interval right here, you can see that the graph is increasing from left to right. That means if we were to check, the first derivative would be positive on that interval. On the second interval, in this little blue part, you can see that your graph is decreasing from left to right. So that means if we were to verify, your first derivative would be negative. And then finally, on this last interval, you're back to increasing. So your first derivative would be positive. In just a few minutes, I'm going to show you how to break these intervals up because that's probably the number one question we get. How do I know where do these intervals start and end and such? We're going to go over all of that in the next few slides. Before we can do that, we need one more term before I can break this down. It's called a critical value. And technically, it's something we've already done at some point, but we did not call it a critical value, but that's what we're going to call it for the next few sections. So a critical value of a function is any number c in the domain of f of x for which the tangent line is horizontal or for which the derivative does not exist. So that's the official definition. To kind of make it a little bit shorter and sweeter, more to the point, you can find a critical number by doing one of two things. Number one, you will take the derivative of your function and set it equal to 0. This is very similar back in, I think it was 1.5, when we talked about horizontal tangent lines. That is what we did. We took the derivative and set it equal to 0. That will be where your critical value occurs. Not as popular, but we will see it a few times. If your first derivative does not exist at a certain number, that number is also a critical point. All right. First derivative being 0, first derivative not existing. That's the two times a critical value will occur. So if C is a critical value, then that means it has to have a critical point there. So if you were to plug the critical number back into the original function, then you would create what we call is a critical point. So as you can see up here on this graph that I pulled out of the textbook, every single one of these C values is a critical value because at every single one of those, you can see either you get a horizontal tangent. So at C1, C2, C4, C7, and C8, all of those have a horizontal tangent line versus at C3, C5, and C6, those are either sharp points or vertical tangents. We talked about back in a previous section, that means the graph is not differentiable there. That's why the derivative does not exist, and therefore it's a critical value. All right, so here's how we combine those last two slides to determine what a graph will look like. So for any continuous function that has exactly one critical value in the open interval, there is two or three things that could happen here. So number one, at that critical value, you could have a relative minimum. You will have a relative minimum if the following is true. So in definition form, it's this. If you have a negative first derivative from A to C, and if you have a positive first derivative from C to B. Most people don't like that definition, but you can write it down. To write it out in layman's terms, let's start right here. If your function is decreasing to the left of your critical number and increasing to the right, that point will be a relative min. So illustratively, it looks like this. If you're going down and then back up, so decreasing to increasing, that point in which it switches is considered a relative min, as you can see from this basic sketch. Doing everything in the opposite way is the definition of a relative maximum. So officially, by definition, if your first derivative is positive on the interval A to C and negative on the interval from C to B, you have a relative max. Or in more layman's terms, if f of x is increasing to the left of C and decreasing to the right of C. So if you're going up and then you decrease, that point in which it switches is considered your relative maximum. So decreasing to increasing is a relative minimum. Increasing to decreasing would be a relative maximum. Now, there will be a chance that it doesn't alternate. So if your increasing and decreasing doesn't alternate, so if it goes increasing and then increases again, that's not anything. Same thing if it's decreasing, then decreasing. That's not anything. So you will not have a relative max at those particular points. If you do have a relative max or min, the word that we will call this sometimes is we will call this a relative extremum, or also called a relative extrema if we're doing the plural sense. So if you see a problem on your assignments that says find the relative extrema, it's just asking you to find the relative maximums and minimums. So this is the big definitions. This is what we're going to do a lot of today to determine maxes and mins. So illustratively, I kind of drew the pictures for you, but just if you want to kind of stop and draw these yourself, here's just a couple more illustrative examples of what I was just talking about. What does it look like to be a relative min? What does it look like to be a relative max? And then the two on the bottom, what are some examples where it would decrease, decrease, or increase, increase, and you wouldn't have a relative max or min? So pause the video if you want to write these down really quick, or you can kind of just look at them. That's just kind of illustrative. All right, so let's get to some problems finally. So number one, I would want you to draw a graph of a function which is increasing on the interval negative infinity to 5 and 12 to infinity, and is decreasing over the interval 5 to 12. So if I'm going to draw a rough sketch here, all these numbers that are talking about increasing and decreasing, remember from the definitions earlier, those are all x values. So the two numbers that I see up here are 5 and 12. So let's say that 5 is about right here and 12 is about right here. Just kind of doing a rough sketch. It says your graph needs to increase on the interval. The first one I see is from negative infinity to 5. So I know that I'm going to start down here, I guess, and I'm going to increase until I get to the number 5. Between the interval 5 and 12, it says it needs to decrease. So I'm going to decrease back down until I get to the number 12. And then from 12 to infinity, you will increase the rest of the way, and it will look something like this. This is one of many ways you could have drawn it. It doesn't have to look exactly like this, but this kind of, once again, we're trying to get these interval definitions and be able to picture what it's telling us. Because we're going to see a lot of words that describe graphs. We need to know approximately what these look like. Now, where you've got to be careful on your homework is where I'll mix definitions in. So what if I wrote something like Draw a graph of a function where f prime of x is less than 0 on negative infinity to 1, and f prime of x is greater than 0 over the interval 1 to infinity. So kind of drawing my x and y axis here again, I notice the only number in the intervals besides the infinities is the number 1. So let's start with this first definition. It says the first derivative has to be less than 0. Well, from earlier, a first derivative being negative means that your interval is decreasing. So you need to be decreasing on the interval negative infinity to 1. So I'm going to decrease all the way until I get to the number 1. This second part of the definition says f prime of x is greater than 0 over the interval 1 to infinity. Well, the first derivative being positive is the definition of increasing. So from 1 to infinity, I need to have my graph increase. And in the end, this looks something like a parabola. So not only do you need to be able to know what increasing and decreasing is literally, you need to also know its definition, because that will be mixed in occasionally in our problems. All right, what about this one? I want you to draw a graph of a function where g prime of x is greater than 0 over the intervals negative infinity to negative 1 and 5 to infinity. And I want g prime of x to be less than 0 over the interval negative 1 to 5. Now, the catch is I'm being a little bit more specific about what I want to happen at those points. At g prime of negative 1, that's going to equal 0, but I want g prime of 5 to not exist. So let's talk about these two new things on the end, because the other stuff we've already done. If the derivative at a number is 0, this means that there has to be a nice horizontal tangent, as we saw in the sketch and the graph a little bit earlier. If a derivative does not exist at a certain value, then that means it has to be not differentiable. So that means that there has to be like a sharp point there or a corner. That's usually the most popular. So at 5, when I draw this graph, I have to make sure that it's not differentiable at that value. So let's draw our sketching. The two numbers I see in the intervals are negative 1 and 5. So I'm going to put negative 1 there, and let's put 5 out there. So this first interval says is that g prime of x is greater than 0, and the first interval I see is negative infinity to negative 1. So that is the definition of increasing. So I'm going to increase until I get to negative 1. Now, since negative 1 has a horizontal tangent, I can draw this the same way. No changes here. On the interval from negative 1 to 5, I need my first derivative to be negative. So that's the definition of decreasing. So I'm going to decrease from negative 1 to 5. Now, the difference is that, yes, from 5 to infinity, I'm going to increase again. But since at 5, I have to not be differentiable, I can't just draw a regular smooth curve. I'm going to have to draw like a sharp point or a corner. So let's do something like that. That'd be an easy fix. As you can see, at x equals 5, it is a sharp point. So while that is a relative min by definition, technically your graph is not differentiable there because a corner occurs at x equals 5. So be aware of that, because that's going to show up occasionally in these problems. All right, so let's actually get to some derivatives now. So number 4 and number 5, you need to be comfortable finding critical values. So I picked out two functions that are going to be similar to what we see in this class, and I would like you to find all the critical values and then classify them as either relative maxes or minimums, which we call relative extreme. So number 4 says f of x is equal to x squared minus 6x plus 1. So to first find the critical value, I'm going to take the derivative of my function, which is 2x minus 6, and I'm going to set that equal to 0. If I solve this equation, so if I move the 6 over by adding, you get 2x equals 6. And if you divide both sides by 2, you get x equals 3. So that is my only critical value. Now, officially, some of y'all might notice that this is a parabola. And we know that parabolas look something like this. So I think we know that this is going to end up being a relative minimum. But just to be official in how we check this, if you want to find out officially if this is a max or a min, we are going to draw what I call a first derivative line graph. And on that line graph, I'm going to plot the critical number that we just found. On each side of the critical value, I'm going to pick out test values. It can be any number you want as long as it's on either side of 3. So over here, let's pick 0, and how about we pick 4 over here? You're going to plug those test values into the first derivative that you found over on the left. You can use your calculator if you'd like, or you can do mental math. We do not care what the number is. All you care about is it positive or negative? Because you're trying to figure out which side is increasing and decreasing. If you plug 0 into this first derivative, you're going to get a negative number, which means your graph is decreasing on the left-hand side, because a negative first derivative means decreasing. If you plug in 4 into the first derivative, you're going to get a positive number, which means you are increasing on the right-hand side. Well, based on our definitions earlier, if your graph goes from decreasing to increasing, then x equals 3, or whatever number it ends up being, has to be a relative minimum. So that means you're going to have a relative minimum at x equals 3. Very good. There is no relative max in this problem, because a relative max, you have to go from increasing to decreasing. Let's look at a second example. So number 5. If g of x is equal to x cubed minus 3x minus 6, what are the critical values, and then can you classify them as relative extreme? So first thing I'm going to do is take the derivative. Oops, I'm going to change color, sorry, just so it's easier to see on the eyes. Let's change this to red. So g prime of x is going to be 3x squared minus 3 that I am now going to set equal to 0. If I add the 3 over to the right-hand side, that is 3x squared equals 3. And if you divide both sides by 3, that is x squared equals 1. Be careful from algebra. If you take the square root of both sides, you probably learn that the square root property says that both of your critical values are going to actually be plus or minus 1. So you'll always do plus and minus when you take a square root to solve for x. You've got two critical values, so when I draw my number line this time, I need to plot both of those numbers in order on the number line. So I'm going to plot -1 and +1, and then I'm going to pick out some test values. How about -2 that's less than 1, 0 in the middle, and 2 over here on the right? You are plugging all 3 of those test values into your first derivative. And like I said, just use your calculator if you need to. So let's see. If I were to plug -2 into this, it looks like you're going to get a positive number. So you'll be increasing. If you plug 0 into the first derivative, it's going to be a negative number, which means you're decreasing. And if you plug +2 into the first derivative, it's also another positive number, which means you're increasing. So going from left to right, at x equals -1, your graph changes from increasing to decreasing. So that means that you're going to have a relative maximum at x equals -1. Versus at x equals +1, you go from decreasing to increasing. So therefore, you're going to have a relative minimum at x equals 1. So this is a good example of where a graph can have both, versus number 4, this graph only had one of them. So it all depends on the problem. There's not a set way. Every problem doesn't work the same way. Just be aware, take your derivative, find your critical values, and then check your line graph to see what you have. Now that we've practiced that, let's actually move into a problem where you're going to actually do the graphing part of it as well. So we got two of these, what I'm going to call longer problems we have to do. So be ready for the next two. Number 6 says, find any relative extrema of each function. List each extremum along with the x value at which it occurs. Identify the intervals over which the function is increasing and over which it is decreasing. So that'll be new. We'll go over that. Then I want you to sketch a graph of the function based on all this information. And we're going to begin with f of x equals 6 minus x squared. So I'm not going to necessarily do all of this in the order in which it says, but we're going to end up finding all of this by the end. Since we got to do all this increasing and decreasing and maximum and minimum stuff, first thing I'm going to do is find the one thing we need to do all of that, and that's the critical value. So f prime of x is going to end up being -1 minus 2x that I'm going to set equal to 0. If you add the 1 over, that will be -2x equals +1. And if you divide both sides by -2, you get x equals -1/2. That's my one critical number. So what I'm going to do is draw a number line where I'm going to plot the -1/2 in the middle, and then I'm going to pick test values on each side. So less than -1/2, I'm going to pick -1, and then bigger than -1/2, I'm just going to pick 0. And remember, from the last slide, you are plugging these into your first derivative. If you plug -1 into the first derivative, you should get a positive answer, which means increasing. If you plug 0 into the first derivative, you should get a negative number, which means decreasing. From this line graph, we can answer almost every question up here. Number 1, we have something new. What is the interval of increasing? So according to my line graph, I am increasing everywhere to the left of my critical value, -1/2. So that would be the interval -infinity to -1/2. And the interval of decreasing would be everything to the right of my critical value, which would be from -1/2 to infinity. We only have one critical value, so we're only going to have one extreme. But since we are increasing and then decreasing, that means that you're going to have a relative max. And this one's a little different because it wants you to find the entire extrema. So since -1/2 is an x value, we're going to write this as an ordered pair because I'm going to have to plot it on my graph in just a minute. So x is -1/2. Since this is just a point, to find the y value of your point, you're going to plug the -1/2 back into the original function. So what I'm going to do is get my calculator out here, and I am going to type this in. Now, you're probably going to get a decimal here because it looks like the decimal I'm getting is 6.25. But you're going to need to be able to have a way to probably put that in fraction form because the homework is picky on some problems where it wants fractions, not decimals. So 6.25 is the same fraction as 25/4. Let's plot our graph. So over here, I'm going to go to the point -1/2 and then up here to 6.25, and that's my relative maximum. And then based on my intervals of increasing and decreasing, I should be increasing up to the relative maximum. And then once you get past the maximum, you should be decreasing straight down. And that is a rough sketch of what 6 minus x squared looks like. We're going to add more pieces over the next couple of videos where we can make this even more precise. But for now, we're just starting very basic and building up our knowledge. All right, so let's do one more just like that. So same instructions. I want you to find all that same information, but now I want you to do it for g of x equals x cubed minus x squared minus x plus 2. So just like number 6, the first thing I'm going to do is I need to find my critical values. So I'm going to find the first derivative of g, which would be 3x squared minus 2x minus 1, and I'm going to set that equal to 0. This one will require you to factor a little bit, so we are going to factor this equation. So let's see, that'll be 3x and x, 1 and 1, and then plus and minus. I'm going to set both of my factors equal to 0, just like you do in an algebra class. The first one, if I subtract 1, that's 3x equals negative 1. And if you divide by 3, x is equal to negative 1/3. On the second one, if you add 1 to both sides, x is equal to 1. All right, we're going to draw our number line down here kind of out of the way. And I'm going to plot both of my critical values on there, negative 1/3 and 1. I'm going to pick out some test values. So let's see, less than negative 1/3, I'm picking negative 1. In the middle, I'm going to pick 0. And over here, I'm going to pick 2. And this is where your calculator will probably play a big role here, because you need to plug all 3 of those numbers into your first derivative. So I've got my calculator out here, so I'm going to do a little number crunching really quick. So let's see, if I plug negative 1 in, you should get a positive answer, which is increasing. If you plug 0 in, that's a little bit easier. That's going to be a negative number, so that means you're decreasing. And if you plug positive 2 in, you should get another positive number, which means you're increasing. And now we can answer all of the questions. So down here at the bottom, I'm going to write my intervals of increasing. So that's going to be everything to the left of negative 1/3. So that is negative infinity to negative 1/3. And it's also everything to the right of 1, which is from 1 to infinity. Now, in an algebra class, your teacher probably taught you that you would use a union symbol between these, and I do agree with that. But in this textbook, when you get to your homework, I believe when I looked it up, they want you to put a comma between them. So just be aware of that. That's technically how they want you to write your intervals. For your interval of decreasing, that's everything between the 2 critical values. So that would be from negative 1/3 to 1. So both of those critical numbers have to be in extrema. So let's write them both out. At negative 1/3, you go from increasing to decreasing. So you're going to have a relative maximum at the point negative 1/3 something. Because remember, negative 1/3 is your x value. To find the y value, you need to plug this into the original function. So let's see what we got here. Negative 1/3 raised to the third minus negative 1/3 squared minus negative 1/3 plus 2. Turn that into a fraction, and you should get 59 over 27. For those who are curious, this is about 2.185. At x equals 1, back on your line graph, you go from decreasing to increasing, so you end up with a relative min there. So we're going to have a relative min at the x value of 1, and then to find the y value, same thing. Plug 1 back into the original, and let's see, 1 minus 1 is 0. Now you should get positive 1. Plot those 2 points on your graph. So if I go to negative 1/3 and then up to about 2.18, that's about there for your maximum. And your minimum is going to be at the 0.11. And then according to my intervals of increasing and decreasing, we're going to increase, then decrease, and then increase. So it should look something like this. We increase to the maximum, decrease down to the minimum, and then increase the rest of the way. And this is a rough sketch of x cubed minus x squared minus x plus 2. All right. I wanted to stick number 8 in here because it's a little bit different kind of derivative. So everything we've done so far in this section has been the power rule, but occasionally we will see problems that aren't power rule, and we have to be able to do those as well. So how about we just, no graphing this time, let's just find and classify all the relative extrema for g of x equals -5 over x squared plus 4. Now, this one you can either do with the quotient rule or you can do it with the chain rule. It doesn't really matter to me. If you do it different than I do, that's fine. I'm just going to do the quotient rule because it's already in that form, but I could easily rewrite this and do chain rule. So quotient rule says I can let the top be f, the bottom be g, and we would find the derivative by doing g times f prime minus f times g prime over g squared. So my derivative, which is capital G prime of x, would be my g function, which is x squared plus 4, times the derivative of f, which would be 0, minus my f function, which is -5, times the derivative of g, which is 2x, all divided by g squared. Well, 0 times that first term goes away. Then you are left with negative times a negative is a positive, so that becomes 10x over x squared plus 4 squared. And for the first time, you're being asked to find critical values of a fraction. And this does make you do one extra step. If your derivative ends up being a fraction, when you find the critical values, the easiest way to do this is you have to set both the top and the bottom equal to 0. So over here, I'm going to let 10x equal 0, and I'm going to let x squared plus 4 all squared equal to 0. Solve them both. The first one's a lot easier. Divide both sides by 10, and you get x equals 0. So there's one critical value. The second one, if you take the square root of both sides, you would get x squared plus 4 equals 0, because you can't do plus and minus 0. If you move the 4 over, you get x squared equals -4, and that's not good, or maybe it is good. It's impossible to have a squared number equal a negative. That doesn't make sense. So the bad news is that there's no critical value, or maybe that's good news. You don't have to worry about that. There are no critical values from that, but you have to check it because there could be some critical values from the bottom of your derivative. Since 0 is my only critical value, when I draw my number line over here on the right for my first derivative, which I guess is g prime of x, I'm going to put 0 right in the middle, and I'm going to pick the test values out of -1 and 1. And remember, you are plugging those both into the first derivative we found over here on the left. If you plug a negative number in, let's see, you should end up getting a negative number, which means you're decreasing. If you plug +1 in, you should get a positive number, which means you're increasing. So since we are decreasing and then increasing, that means you have a relative minimum at x equals 0. And just to practice this way again, we can write this as a point. So I know 0 is the x value. You'll plug the 0 back into the original function to get the y value. So if you plug 0 back into the original, you should get a y value of -5/4. So therefore, your only relative extrema is a relative min at the point 0, -5/4. Big thing to get from this problem before I go on to the last problem for this video. When you take the derivative and it's in fraction form, you have to set both the top and the bottom equal to 0, or you may miss a critical number. All right, so let's end with a nice little word problem here. So number 9, a hotel owner notices that she rents Y rooms per night when the price is X dollars per room, with Y equaling 200 minus 2X. Find the revenue function, which is the total revenue generated per night when the price of each room is X dollars, and then find the relative extremum of R and interpret the result. So if you remember back in a previous section, we talked about how to find a revenue function if you don't have it given to you. So what we can do here is to find the revenue function. We are going to take the variable X and you're going to multiply it by the function that you are given, which is 200 minus 2X. Well, I think we saw this back in section 2.3, I believe. I think it was one of the last problems in that section when we did this. If you multiply this by X, this gives you 200X minus 2X squared. So this is going to be your revenue function. And once again, it's in terms of X, so we're on the right track here. Part B says, find the relative extremum of R and interpret the result. So to find the relative max or min of R, we have to first find the critical value of that. So I'm going to take the derivative of my revenue function, which will be 200 minus 4X, and I'm going to set that equal to 0. If I move the 200 over, that is negative 4X equals negative 200. And if I divide both sides by negative 4, you should get X equals 50. If I draw my number line, so that will be 50, and I pick out some test values, how about 0 and 60? Those sound good. We're going to plug those into our first derivative over here on the left. So remember, this is your first derivative line chart. If you plug 0 in, you will get a positive number, which means you're increasing. If you plug 60 in, it looks like you're going to get a negative number, which means you're decreasing. So since you are going from increasing to decreasing, that means X equals 50 will be a relative maximum. So this means that your revenue has a relative maximum at the point 50, and then just like earlier, if it just asks for the 50, you're done. But if it wants the whole point, you have to plug that 50 back into not the original problem, but the original revenue function that you found. All right, this would be 200 times 50 minus 2 times 50 squared, which would be 5,000. So according to this, your revenue will be maxed out when you sell $50, when you charge $50 per room, and you will make $5,000 of revenue per night, and that will be your maximum. So that ends the video for section 3.1. We talked about how you can use first derivatives to find max and mins and do a little bit of sketching. In the next section, section 3.2, we're going to bring in the second derivative and talk about what are some other things it can tell us about graphing functions.